Hi class, this is Professor Smith. I'll be doing a movie on inferring properties of a polynomial function from its graph. So here we have the graph of a polynomial function, and we want to be able to answer the following questions. The first question asks about increasing over an interval, and I believe I might have mentioned it in our class, but just in case, we can think of our curve as a roller coaster ride. And as we're growing on our ride on our roller coaster, we can pretend like I'm a little um, ant or yourself on a roller coaster on your Lego truck or Lego roller coaster. And so as I'm moving upward on the graph, then that's considered increasing. And the reason why is because my functional values are getting larger and larger and larger as I'm going up on the graph. And then I'm riding my roller coaster down, and at -8, I start to drop down. And then at -2, it looks like I'm going to go back up. And then at x equal to 5, I start to go back down. So the intervals where it's increasing is where I'm going up on the roller coaster. And so we want to know the x values where that behavior is occurring. So the x values are from -infinity to -8. So from -infinity to -8, the graph is going upward. So we'll click that box. And -infinity is just a symbol for saying it decreases without bound. In other words, we have the box cutting off part of the graph, but this is indicating that if a box wasn't cutting off, that it would be decreasing forever to the left or without bound to the left, which we call decreasing without bound. And then again, we're going down from x equal to -8 to x equal to -2, and then we're going back up again from x equal to -2 to this x value of 5. So we'll select that interval. And then we're going back down afterwards. So those are the intervals where it's increasing. So sometimes the function may ask where it's decreasing, not where it's increasing. So you want to be sure to pay close attention to the terminology. And then I ask the function where it has a local maximum at which values. So local maximum means that if I were to cut off or shade off part of the graph, in that part where it's not shaded, is it the biggest guy? So we can see here that at x equal to -8, we have a maximum or a high point at y equal to 5. And so that maximum would be 5. And this one asks where it occurs. So it has a maximum and it occurs at x equal to -8. If it asks for the maximum value, then we would put in 5, but it's asking where it occurs. So if we look here at -2, it's downward, so it's a low point, so that wouldn't be considered a maximum. But when we go to 5, it is considered a maximum. It's the biggest. So x equal to -8 and x equal to 5 give us the two places where the local maxima occur. What is the sign of the leading coefficient? So what I'm going to do for this one is I'm going to open up Desmos so we can take a look at two very familiar curves, y equal to x squared and y equal to x cubed. So I've opened up Desmos.com. This is also an app that you could download on your phone if you wanted to. So I'm going to start graphing and graph two very familiar functions. Let's graph y equal to x squared. And I got the exponent by hitting Shift 6. So Shift 6 after the x and then typing in 2. So that gives me y equal x squared. And that is a very familiar function. If we look, we notice that both of the ends of the parabola are going up or increasing without bound. So you can think of it as a cheerleader holding their hands upward and making a V with their hands. That is representing that parabola. So both are going up. You said, well, what can I do so that it would go down? Well, if I change the leading coefficient from 1, which is x squared implicitly has the leading coefficient of 1, if I change it to the opposite of x squared, notice my graph, it flips downward. So notice with the even exponent, They either both go up or both go down. So now let's graph y equal x cubed. So again, shift 6 and cubed. And in fact, I really could graph y equal to x, but let's stick with x cubed. I'm going to select the color red for that y equal x minus x squared, and I'm just going to click it, and that'll get rid of the graph. I can also change the color. So now I'm just looking at y equal x cubed. So you notice with this graph, it rises to the right. And the reason why is when you substitute in those positive values, when you cube them, they still stay positive. So 1 cubed is 1, 2 cubed is 8. But when we plug in those negative values, at -2, we get -8. So that's why it falls to the left. So it rises to the right and falls to the left. The same is true for y equal x. Uh-oh, let me do that on a different line. Y equal x also rises to the right and falls to the left. So whenever we have odd exponents, they're going to rise to the right and fall to the left if that coefficient is positive. So let's change this one to a negative x cubed. And so with a negative x cubed, it flips. So now instead of rising to the right, it rises to the left. And you can think of it this way. Negative numbers are on the left-hand side of the axes, y equal to 0. And so that's why you can think when it's a negative leading coefficient for an odd exponent, it'll rise to the left. When it was positive, in the case with y equal x cubed, it rises to the right. So odd exponents rise to the right. Odd exponents with a positive leading coefficient rise to the right. Similarly, if I put not a subtraction, but if I take the opposite of x, same thing, it rises to the left. So when that coefficient is negative, it rises to the left. I'm going up on my roller coaster, rising to the left. And then I just want to show you what it looks like when we have y equal x to the 4th. Because that's just another even power. It looks very similar to x squared, except it flattens out at 0, and then it rises really fast. So that's y equal x to the 4th. So let me get rid of the cube ones and add back that x squared, and let's make it positive as well. So you see how the purple graph, let me blow it up just a smidgen, how it flattens out until you get to 1, and then it increases very steeply. But again, notice both ends of the graph are both either going up, and of course if we want it to go down, we can change this to -2 x to the 4th. I don't want to make it -2. It'll be so small you won't even see it. Let's do -1/2. All right, so now we have -1/2, and so you can see now it's going downward. All right, so I hope this little brief step aside to look at Desmos to know the behavior or the end behavior of a graph based on the even exponents by using just 2 examples, with the even exponent of 2 and 4 and the odd exponent of 1 and 3. All right, so let's go back to our problem. So for our graph, it's going down on both ends, so we know it's even. Because it's going down, we also know that it's even with a negative leading coefficient. So we need to capture that it is even, so remember that it's even. The next problem asks, which of the following is possible for the degree of f? So here we have that this particular curve has 1, 2, 3 extrema. So if it has 3 extrema, then we know that the degree is 1 more than that. So that means the degree could be 4. Four is even, so we got to remember that. But what's another number that's even, that's bigger than 4? 6 or 8. All right, so we're going to use the fact that it's 1 more, but it has to be even. So let's say that our problem had 4 extrema. That's better, 4 extrema. So the degree has to be at least 1 more. So it would have to be 5. But 5's not even. So that means I have to bump it up to 6. Let me say that again. So if I had 4 up and downs, 4 extrema, the degree has to be 1 more than that. Could be more than that, but at least 1 more than that. So 1 more than 4 would make it 5. However, we know that this won't work being a 5. It has to have an even exponent. So I have to go, well, what's an even exponent that's 5 or more? And an even exponent that's 5 or more would be, in this particular case, we would pick 6 and 8. So let's check to make sure we're on the right track. Hot diggity dog we are. Let's go ahead and hit more practice. By the way, the fact that the polynomial has to have a degree at least 1 more than the number of extrema, that's something we prove in calculus. All right, so this next one, we have our graph. Let's make it just a little bit bigger so you can see. All right, so this one is asking where it's decreasing. So now we want to know when we're going down on the roller coaster. So I can see I'm going down on the roller coaster in this region here, and the corresponding x values, I'm going down from -9 all the way till I get to -5. I'm also going down on my roller coaster in this region where x falls from -1 to x equal to 5. And then I'm also going down on my roller coaster from x equal to 9, and then it keeps going forever, and we write that as positive infinity or increasing without bound. It asks where this function has local maxima. Those are the high points on our graph. So I have a high point here, and that's going to occur at x equal to -9. It has a high point at this value here, and that high point is occurs at x equal to -1. And notice that I'm separating each of the places where the extrema or the max occur with commas. And then that's a low point. So here I have another high point, and that occurs at x equal to 9. Oh, this is identical to the last one. Shoot. Oh, well, that's okay. We know that because they both go down, that it's going to be an even exponent, and it's going to have a leading coefficient that's negative. We'll do one more. And then we have how many extrema? I have 1, 2, 3, 4, 5. So then I know the degree is 6 or more. So if the degree is 6 or more and it's even, then it can be 6 or 8. So remember what I did? I counted that extrema. I had 5 of them. 1, 2, 3, 4, 5. So add 1 to 5 is 6. So the degree is 6 or more. Has to be even. So it's going to be 6 or 8. We'll do one more. Hopefully it won't be an even one. Yippee! Correct! All right, let's do one more. All right. So this one again is asking for decreasing. So here I'm going up on the roller coaster. Poof! I start going down. Yay, the fun part going down. Actually, the fun part's going up too. So it's from -4 to -1. We're going down. We're going down again from x equal to 3 to x equal to 6. And then from there on we're going up. Now in this particular case, we're rising to the right and going down to the left. So if we recall from our Desmos graph, that was going to be an odd function, odd exponent. Y equal x cubed, it rose to the right. Because it's rising on the right, I know that the leading coefficient is positive. So let's hold on to the fact that it's odd. All right. Here they're asking us the x values where we have local minima. So low point. So these are low, and so x equal to -1. Here's a high, and here's another low at x equal to 6. So the last one asks the degree. So we have how many extrema? 1, 2, 3, 4. So I know the degree is going to be 5 or more. It has to be odd. So since 5 is odd, we can start there. So it can be 5 or 7 or 9. So I hope this movie on inferring properties of a polynomial function from its graph was helpful for you.